Okay, so right, sorry, background on right. This is like the background on who we are, but we kind of structure this as a virtual machine learning lab that people show up to. They need machine learning models that are built. They get built by this virtual lab of agents and then delivered back to them. So starting a little bit of background on.
Sorry, could you move a little so for like the podium so we can see the.
Yeah, is this better?
Yeah.
Okay, excellent. Okay, so the first major breakthrough in this kind of field of AI agents or AI systems doing end-to-end machine learning research was by Chenglei Sei. This can LLMs generate novel research ideas about a year and a half ago, and this was just evaluating the LLMs at the time for how novel the research ideas were that they were creating with a relatively straightforward harness. But this is like a very open-ended task where the agents are just supposed to read papers and come up with the next paper and have some novelty to those. You guys are all probably familiar with Sakana's AI Scientist, but it then extends this further into creating like LLM ideas, novelty checkers, coming up with experimental plans. All of these are specific, like a lot of these were specifically in the machine learning domain. So trying to come up with the next innovation in some machine learning task, and then actually implementing it. And then the last step is writing up the result into something that looks like a paper. So something that I worked on and that we worked on at Autoscience was getting the systems like this in order to actually create papers that could pass peer review. A year ago now at ICLR sent three of the papers that were created by our system Carl to ICLR workshops, and they were accepted there. I like to say that they were the first like AI generated research papers to pass peer review. Like a week later, Sakana did their thing and got like 20 times as many likes as we did, but that's what happens in research, so it's okay. But the main again, this is all like none of this exists inside of any kind of closed loop harness. This is all just single pass through, like trying to get an AI system that on one shot can just create these high quality outputs. So then obviously fun search starts to get really interesting in these paradigms. So if you can take a system like this and put it into a fun search like harness, you can actually start to get really interesting results. If in case you guys didn't, the fun search was talked about in the last talk, but it's just the very simple idea that you can evaluate a proposed piece of code for how good it is and then keep what works and go back. AlphaEvolve, when it came out, two of their four main examples were actually on machine learning tasks. One of them was on schedule, like GPU scheduling, and the other was on kernels, and are now being used to train Gemini. In this case, they isolated specific portions of the code base which were responsible for like specific GPU scheduling, and then were able to optimize over that using these methods. This was kind of like a very early sign of life of algorithmic agent harnesses beginning to make progress on AI research and development. So the main challenge that comes up in AI tasks, among many others, is that the evaluation is expensive. When you start scaling this up to when you start using techniques like this, where you want to have hundreds or thousands or hundreds of thousands of experiments that are being evolved over, but every single validation step requires training an entire model on dozens or hundreds or thousands of GPUs, the costs become unbearable. So there's a few other kind of unusual things that come up as you start focusing on machine learning tasks. A big one is underspecification of the problem. People come to you and they say, I want a better model, or I want a faster model. And what they actually mean is, I want a model that's better, and I'm okay if it gets a little bit bigger, but not that much bigger. And I'm okay if inference slows down, but not that much. or like accuracy, like I want more accuracy, but I'm not okay with more training time. And none of this is really well specified. And so, and so you can end up in a situation where your accuracy improves, but you have a machine learning model that's unusable. The environment is also very different than the other tasks that we've been seeing. When you're creating solutions to like circle packing or 2048, all of your solution space exists in code. That ends up being very different in ML tasks. Like you have kernels that need to be compiled and very large data sets that you need to access that you can't just like put on your file system. And all of these challenges this is like it adds an entirely new part of the solution space that you need to think about. There's also delayed feedback. Like training runs are very long. And so even just tuning a system that does this it's like tuning those hyperparameters that Henrique was talking about is like a week for a single run to see whether or not those hyperparameters are better or worse than before. And then also, I'm sorry, the state continuity is the same thing. But like and then of course the other thing about delayed feedback is that it's very expensive because delayed feedback means that you have all this idle time, and idle time means GPU is like many GPU hours that you're losing. So the thing that we found to be most helpful in tackling these was actually like training at test time. So this allows vastly improved sample efficiency. Like what we care a lot about is this question of how good can we make an ML model with a specific budget. And so when you train at test time, which the TTT Discover guys did a great job talking about in their paper, you end up creating a model that's better at operating inside of one of these like evolutionary search harnesses like OpenEvolve or AlphaEvolve that we saw before. And the sample efficiency improves meaningfully, which maybe doesn't make, like when you're talking about circle packing and it's a difference between like $6 and $30 in which model that you're using, that's like it may not make sense to train a whole model, like the training might be more expensive, but when you're doing this for machine learning tasks, it ends up becoming very important because most of your cost there is going to happen at the exploration time and not on the training time. That said, TTT does kind of introduce this unfortunate collapse of diversity. So if what you're really looking for is novel ML breakthroughs, TTT isn't really going to get you there. It causes, at least what like my understanding of this now is that it causes somewhat of collapse in like the creativity of your model inside these RL harnesses, and some of this is even still seen on these initial passes through the model. A lot of the early results that people thought that they were seeing on the first two papers that I talked about with Sakana and I can't remember what it was called, Chenley's paper about novel research ideas. Turned out that most of the good research ideas weren't quite as novel as people thought. Like it's just really hard for humans to identify what is novel and what's not. And so those initial pieces, it's now been found that they really just like, they weren't quite as novel as the ideas that made it through all the re-ranking steps. Those last ones, they made it through them because they were good ideas that kind of already existed in the training data of the models. So after going through all of this TTT, we have our system, which is called Mira, and we evaluated on our benchmark, which is it's like roughly a combination of Kaggle competitions. Claude Code by itself is kind of in the 13th percentile. OpenEvolve was at 34th, and Mira is at 96th. That said, like this isn't a reflection on either of these two, and I have great respect for the folks who worked on OpenEvolve. Like this isn't. I feel like sometimes people do this and like look at how great a thing is. Like no, it's like this was meant for a very different kind of task. Mira was optimized specifically for machine learning tasks, and so it works really well on those. But yeah, we've used it to like win Kaggle medals, and our team has we've won Kaggle medals and things that we have no expertise in. You just we throw the system at the competition, and enough compute, it does really well. At least for me, I really enjoy working on this because I think this is the route towards recursive self-improvement. We've seen signs of life of this initially in the new Minimax model. They had pretty much their entire blog post was dedicated to how they had a very similar harness that was used to optimize Minimax 2.7. And they claimed that it had a 30% improvement on their internal eval, but they didn't really say what the internal eval was, so I don't really know what that means. But apparently it had hundreds of rounds of training new models that eventually got integrated into the latest model release. So internally, my goal is to use this to create much more sophisticated base models. So we are hiring, if anybody's interested. This is the last plug, last slide. But yeah, if anybody wants to work on this to work on these systems to make new and better ML models that maybe can then make these systems better, please email us. Yes.
So I'm curious about the training at test time.
Yeah.
The expectation of the policy there, the expectation of the policy there was the model's own policy, right?
The expectation of the policy, sorry, what do you mean?
In the iterates, there's an expected value over, I think like ABC, what loss and use.
Yeah.
There's an expectation of loss function. It looks like it's actually chosen by the policy, right?
So we have. Sorry, I'll jump back to that here. I mean, I guess it's not even so clear, but yes.
Yeah, that's the model's own policy. That's not a baseline policy. That's not an aggregation policy.
Yes, that's right.
Okay, so that seems like it could explain why you get a collapse in diversity.
Right. It's like not unexpected that would happen.
So is there an exploration policy that's used in this case, or what's the vibe?
I mean, it's like, so there was a lot that I could say if this weren't recorded. I really wish I could. We should talk after. I would love to get into that. Yeah, I think there's, yes. There is, yeah, this is like a very toned down version for what I could put on YouTube, but I would love to, it's very cool and I would love to talk to you about that after. Yes.
Cool.